and I typically keep 5 PhDs there for PHM and reliability studies. And the other team mostly works on motor drives, design and control. People mostly knows us, our studies about the reliability, but we do extensive motor control as well. So why do we work on the reliability? Because if you look at the problems of the systems in general, power electronics seems to be the champion of the issues. And if you look at the power electronic and zoom in the issues component level, you do see that power semiconductors and capacitors are the, again, champion of this game. So if you look at these charts, for instance, 59–60% of the issues are caused by the inverters. By the way, this belongs to a solar farm survey for 5 years. Okay, and among the issues, 60% is reported as a power electronic issue. And if you look at the issues of power electronics and granulated, it's like mostly power semiconductors and some capacitors. So this percentage can be different from application to application. But since we've been passing through the major part of the power through the power semiconductors, those are naturally the most vulnerable components in the system. And for instance, some of my sponsors from oil and gas, if their system fails during a well operation, they lose $1 million per day. So that's why they like to monitor the system very well, and they want to make sure that the system can finish the mission. So before the mission, they want to make sure that it's healthy, and they don't expect any issues during the well operation, which may take few days. And these systems are mostly in the middle of nowhere, so replacing them is a painful procedure. So another thing, EVs are another concern. So most of the issues in today's traditional combustion engine vehicles, there are tons of sensors, and if there's an issue, they are reported to the dashboard, and engine light turns on. In EVs, powertrain, unfortunately, this technology is not there yet. So when there's an issue, from on the motor side or inverter side, power semiconductors, capacitors, unfortunately, they can't report this to the dashboard as of today. And this is an issue, and we know that there was a major recall from Tesla. This was a silicon carbide issue, a third quadrant problem. And they had to recall more than 100,000 cars. And the problem there was all of a sudden they were losing the power. So you're driving in the highway 70 miles per hour on, and all of a sudden the power goes. And you of course lose the control. That's a big problem. And this is a bigger problem for aerospace, of course. And if you look at left-hand side, so this is for ZVS systems, typical OBC, DAB or resonant converters. And here also, if you look at what creates most problem, they're also power semiconductor. So that's why these are some of the motivating slides why we are working on this. And I do see increasing number of people interested in this from industry. Every month or two, some companies reach us and ask us to help them regarding condition monitoring, health analysis, REL estimation, or reliable design, or identifying the weakness of the systems. So this is the summary of my research. By the way, most of the slides in this presentation corresponds to one paper or one project. So this is a very high-level summary. If you have any question, you can stop me and ask your questions anytime. Okay, so I classify my research, at least the reliability research, in 4 folds. So the first part is accelerated aging tests and precursor identification. So here in this first level, what we do, we design accelerated aging test setups. There are maybe 10 different tests step you can identify and use for a given application to trigger the weaknesses in a power semiconductor. I'll talk about them later in the next slides. And then once we design the setup, we put like 10, 20, 40, whatever number of power semiconductors and start accelerated aging. And every day or two, we take the device out and put in a curve tracer and then put in an SEM, scanning acoustic microscope if necessary, and then put it back to aging setup. So this loop takes like typically 2 weeks to 2 months. So we age the device and collect the parameters and see how they are changing, why they are changing, and we try to understand the physical roots of it also. And typically at the end of the test, we do failure analysis. And for this, we kept the device, we do cross-sectioning, and there are like lots of different techniques to understand the physical failures and root cause of the problem. We do use I'll show in the later slides different advanced tools to understand the gate-related problems or package-related problems. And then we correlate these physical findings or distractions with the parameter changes that we collected through curve tracer. So this is the first setup. This is the first step. In this first step, again, we do observe the reliability of the device and weakness of the device. Second, we do collect the parameters and see how they are changing and try to understand why they are changing. And in the next step, we do design condition monitoring circuits or software. Okay, so based on the findings in the first step, since we know which parameters are changing and how they are changing, we are trying to probe them and keep track of those parameters in real time. So these solutions, condition monitoring circuits or software, typically the best place to locate them is a gate driver or a microcontroller. Typically gate driver is the best place. So the companies, some of the companies I've been working with, they are semiconductor companies, and whatever solution we provide them, they can put it in gate driver. So the gate driver becomes a smart gate driver which can control and monitor the power semiconductor. So and in the third step, we do remaining useful lifetime estimation. So this is not the best solution, but if the companies or user or customer, whatever you name it, cannot do second step, because second step is the golden solution to me. Okay, then we recommend them to do RUL estimation. It's better than nothing. So in RUL estimation, basically what we do, depending on the usage, how aggressively the device being used, we do try to estimate the remaining lifetime of the device. Now, let me give you a simple example. Like imagine a motor drive. A typical motor drive, if it's used for fan or pump application, the lifetime of the drive is 20 years. Okay, and this is a fair estimate. Now, if you take the exact same drive and use it in a low speed, full load application, okay, then the exact same drive may fail in 2 years rather than instead of 20 years. So because at low speed, full load conditions, like your thermal delta T's, the temperature settings will be way more remarkable and slower, and that will physically cause some disruption in the device. So that's why if you're continuously running or mostly running the system at low speed and full load conditions, instead of, again, 20 years, the exact same drive can fail in 2 years. Okay, so if you know the operating conditions, okay, then you can create a RUL smart meter, and that can count the days of the device, okay, and provide you the remaining lifetime of the device. So I can give you more examples, but I think it should be clear enough, and I have some other slides we can discuss there as well. And the last step is lifetime extension. And in the lifetime extension, what we do, if we notice a weakness in the device from step 2, okay, And what we do, we want to make sure that the device does not fail till the end of mission or task. Okay, so for instance, if this is an EV, and if you notice a weakness, then we change the control scheme or PWM scheme just to make sure that the weak device has less stress and it does not fail till the next possible maintenance. So for instance, in that case, you can let the driver to drive to mechanic, okay, and during that short time, you can change the control algorithm or the modulation scheme so that that weak device does not fail within that time period. Or again, if it's a oil and gas application, you don't want it to fail in the middle of well operation. So again, you change the control or modulation and make sure that that device does not fail till the end of operation. Again, this last fourth step, it's not meant for continuous operation. This is for emergency cases. If you notice that something is coming, it's clear. You want to make sure that it doesn't fail while you're doing your last final test till the next possible maintenance, or you can drive to the mechanic your car, and you want to make sure that this algorithm helps you to make sure that it does not fail while you're driving to the mechanics. Okay, so it's a very short time relief, not long time, long term. So let's go back to the first step. In the first step, as I mentioned to you, like we do design different aging setups, and the tests are listed here. So these are some of the tests: HTGB, HTRB, DC cycling, AC cycling. So depending on the user, how they use it, their concerns, or operation concerns or reliability related concerns. So what we do, uh, we identify some of these tests, okay, as the accelerated aging test, and then design the setups, and then start the aging tests, which takes typically 2 weeks to 2 months again. And if their concern is about packaging, then we like for instance suggest DC cycling or AC cycling. If they are more worried about gate oxide related problems, then again HTGB, HTRB, HTOL, like these are the better options. So again, this is very application specific. We listen to customer and understand their operation details, and then we suggest them a list of component tests, and then we design those setups and start the aging to understand the reliability of their system. So again, we classify the issues into two folds. One of them is package related. So this is well known. The package related problems might pop up in multiple places, as you can see here, like different solder issues, delamination issues, or bonfire, lift or cracks, voids. And typically the power cycling tests are the best to trigger these kind of issues. And the other one is gate oxide related problem, or another one, third one. I typically don't mention it as a third one because it's a minor body diode related issues. So these kind of issues, these are typically can be triggered with the test on the right hand side column, like these columns: HTGB, HTRB, HTGS, repetitive, unclamped, inductive circuit tests. So again, depending on the use case and the concerns of the user, we select some of these and then apply aging and trigger the weaknesses in the device. So this is for instance one of the setup we designed for power cycling. It's fully programmable, and as you can see here, there are 48 cells, and you can age 48 devices, IGBT or silicon carbide, simultaneously. And each and every cell here, they have dedicated microcontroller. So every cell can be programmed independently. And these microcontrollers, they do talk to each other. And it's not clear here, but there is a fan behind the cells. So what we do, like, with the active current, we heat up the device without easing, and then with the fan, we cool it down. Heat it up, cool it down. So this, I mean, they apply tens of thousands of cycles like this. And again, these cycles, thermal cycles, they're programmable. The frequency and the amplitude of the temperature can be programmed. So these tests mostly meant for package-related issues because of the shear stress, because the coefficients of each and every material in the device are different. So that's why when you heat it up with the current, by the way, heating up with the current is the most natural way. We don't use oven. That's not very natural, at least in this DC cycling tests. So we heat up with the current and then cool down with the fans. And because of the shear stress caused by the different material coefficients in the device, like the trigger package related issues. Is there any questions so far?
Yeah, maybe I can. I was noting down some points, so maybe I can go ahead. So last slide, Professor Bilal, you mentioned that there are various sorts of failures, like packaging related and internal to the die itself. So when you are designing the tests, I mean, how do you go about do you try to sort of isolate case by case, like if you're trying to investigate package related possible failures, do you apply a different type of test? And if there are certain gate oxide related failures, are there other type of tests like thermal cycling corresponds to something and HTGB or HTRB corresponds to something else? Like, is there a clear demarcation there?
Yeah, I mean, these are again depends on the sponsors or customers, companies like request, if they want to granulate them and clearly see whether it's gate related problem or like package related problem, we define the test accordingly and we classify them clearly. But some of the customers or sponsors, like, they don't care, like they just say, let me know whether there's a problem or not. Should I replace it or not? I don't care whether it's like package or gate. So in that case, we may bypass some of the details, but for the sake of research, we typically go to details, verifying details. And I'd like to see, the issue package or die. If it's that package, like, where exactly the problem. So if it's gate oxide, so which part of the gate or channel is causing the problem.
Right. And what physical variable are you sort of monitoring? For example, maybe RDS on is increase in RDS on could be something, but how do you correlate it with, let's say, stress on a bond wire? How does it manifest? What is it you're looking for?
Those are typically known. Unfortunately, I don't have a slide regarding that here. So what we collect, typically we collect on-state resistance, VTH, leakage currents, sometimes capacitance, body diode forward voltage drop, for instance. So pretty much all the parameters are collected because we are using curve tracer. It's automated. That's not a big deal. And some of them are useful, some of them are not. Now, if you want to do condition monitoring, it should be easy to implement on a power converter. So, and like some of the easiest ones to monitor on a power converter is VTH, for instance. So that's one of our most popular precursor. And the other one is on-state resistance and sometimes gate leakage current. That's another one. We also did body diode forward voltage drop. So these are some of them. And how these are related to like package or die related issues, this is also somehow known. Like VTH, for instance, mostly caused by the gate related issues. On the other hand, RDSON, I think I have a picture regarding this. RDSON can be both channel and package. So if you want to decouple what is what, you can do it. Like if when simply by looking at the RDSON, with some simple tricks, you can see whether it's caused by the package related issues or channel related issues that can be seen as well.
Right, right. Okay,
So it
interesting.
all depends, like, how deep you want to go.
Hmm.
But yeah, it can be done.
Okay, okay. Thank you.
So this is another aging setup. This is an AC cycling setup. AC cycling is the best of best. Okay, because, like, you can stress both the package and gate related issues when you're using AC cycling, but it's kind of difficult to implement compared to others. So here, this is a EV traction system, at least mimicking that system, and accelerated aging part is, like, test setup is the green inverter, three-phase inverter. So we age the devices on the green inverter. Since the power level is too high, it's not easy to burn the output on the passive loads. Pumping it back to grid is also not that straightforward. So that's why what we did, we put another inverter on the right hand side, and through the inductors, the power goes back and forward. So in this case, like, we just feed the losses. So if it's like a 98% efficient, uh, I mean, typically with 1 or 2 kilowatt power level, you can mimic the very high power application. You just feed the losses, and the main power is cycled in between two inverters. Okay, so this is how it looks like, the setup. So these are the inductors in between two inverters. So each inductor is the 80 kg. They're heavier than myself. And again, these are used to cycle the power back and forward in between two inverters. And again, the main motivation is not to burn the power at the inverter, like left-hand side inverter. That's too much power. It will heat up the room, and it's too much, I mean, waste of power. So that's why we abstain burning the power simply by adding another inverter on the right hand side. And for cooling, of course, it's a big system. Air cooling is not enough. We used liquid cooling, and we tested some of the gate driver features on this setup designed for EV applications. Okay, so here in this setup, like, you can both age the device, or if you have a solution, you can test it on the system. Like, for instance, if you have a condition monitoring circuit that you want to test, you can test it on the system. This is another one. I'm talking about accelerated aging setups right now. Okay. Again, this is a very high level summary. This is again setup, and we did the age toll test, actually dynamic age toll. Okay, high temperature operating load conditions. So here, what we're trying to do in this particular setup, we do age the GAN devices, we stress them. Okay, so what we have on this PCB, the GAN device is underneath this power resistor. And the power resistor here is installed here to heat up the GAN device. We call it micro heating. And the temperature of this power resistor, we control it. It can go to, like, 125, 150s. And the reason we use this instead of oven is because the 150, for instance, is a very high temperature, so most of the ICs on this PCB will fail. Okay, so that's why we just want to heat up just the GAN device through this power resistor. And this one is designed specifically for soft switching a QR flyback system. And we wanted to test some of the transient reliability issues at max temperatures, max voltage, and full current for QR flyback systems. And we want to see how dynamic hold state is affected. I think I have a few more slides about this. I can explain later, but this is also very application-specific circuit. And the challenge here is, as you can see, like, one PCB per GAN. That's a very complicated setup. And because, like, in order to monitor dynamic on-state resistance in real time, which is really very challenging, We had to use like high-speed ADCs and DACs to stream the data. Okay, so these ICs are the ADC and DACs. We have a microcontroller for each board, dedicated microcontroller, but the ADC of the microcontroller is too slow for this application because we are talking about dynamic on-state resistance, and you have to sense the current and voltage to calculate the dynamic on-state, around 100 nanosecond. So typically a microcontroller ADC, including sample hold and conversion, may be like, more than 250 nanosecond. So, and if you're doing it multiple channel, it's even slower. Typically, MCU ADC is like slow for this kind of setup. So that's why we use dedicated ADCs, high-speed ADCs. And the purpose was again to monitor dynamic on-state changes. Okay, dynamic on-state resistance. If you want to do like static on-state resistance, for instance, then you don't need this kind of complicated setup. Or VTH, for instance, not maybe for again, but for other devices, again, the circuit can be way simpler than this. Okay, this is another setup, and in this setup, we tested a silicon device, and here in this setup, we were able to test 36 devices, each 36 devices in an accelerating manner. So these are LDMOS silicon devices, and we conducted 3 different tests. And in the first test, we were applying 8 billion avalanche pulse per day. So this was meant for high power density application, LDMOS. I think those are mostly used for like some memory applications, some data center applications. And when you design it for high density, then you may hit the limits of the device and push it maybe even further. So we wanted to see the reliability of the devices under avalanche conditions, and we were applying 8 billion pulse per day and still was surviving. And I think each test took like 3 months. So that's quite high. I mean, these are very robust devices. And here, we tested the reliability of some of the isolation barriers used in this device. These are integrated into ICs, LDMOS devices, and we wanted to see like which isolation configuration is the most reliable under these conditions. So these are the accelerated aging setups. I just wanted to give you some flavor about the setups, okay, and show what they look like in general. Like we designed, way more than these. I don't want to show all of them. And then, as I mentioned, we do collect the data while we are testing, and then we do FA analysis and try to understand why these parameters are changing and how we can correlate it to physics, the failure analysis of the device, each device. This is very, very important for research findings. And here is another snapshot. So these are package related issues. As you see, there are some cracks on the bonfires or on the solders and some liftoffs. And as you can see in this picture here, this is the on-state resistance. Okay, now it's gradually increasing. This is the cycle, number of cycles. So it's gradually increasing. So why this on-state resistance is increasing, it's hard to know whether it's because of channel or package, unless you do some specific or unless you apply some tricks. It's hard to know. This is combination of channel and package. Now, if you want to decouple them, you can decouple them. If you look at it, partial VGS, for instance, you're going to see channel-related issues which will dominate too much. Okay, like instead of applying like 15 volt or 20 volt to the gate, if you apply 5, 6 volt, for instance, or 7 volt, whatever, and look at the same graph, for instance, in that case, any change corresponds to channel because you've been significantly amplifying the channel resistance in linear mode. Okay. When you go to the like switch mode, then you see the combination of channel and package. But in switch mode, like the channel resistance is not that dominant. Okay, so you can decouple the package related issues and die related issues when you like look at on state resistance. That's what I'm trying to say. Uh, it's not straightforward, but it can be done, and we did in some of the studies. And there are some jumps here. So these jumps correspond to these cracks. Okay, so when you have a lift off or a big crack somewhere, as you can see, it's jumping. So you can put a threshold and you can say, okay, if it's more than 10%, 15%, that's too much. You can force user to turn off the system or replace the power module or power semiconductor. But I mean, you see it, right? I mean, it's gradually increasing, and then once you have package-related issues, I mean, it's like directly jumping. Any question here or so far?
So in this graph, Professor Bilal, this different colors correspond to different types of devices. What?
Yeah.
I mean, different samples. Just is it?
That's correct. Yeah.
So what explains that some of them? I mean, are they just different devices? I mean, I see there's some variation. Uh, is there different type of devices or devices from the same different batches or lots, or what is the difference?
These are devices, same devices from different batches.
Okay.
I can't remember the details, like because we run, tens of maybe hundreds of tests. So this is only one of them. But typically, like, we randomly select from different batches and put them on the setup and compare them. Like these looks like from the same vendor, different batches. But even in the same batches, like, this kind of differences like normal.
Right. Okay.
Okay, so once you know how the parameters are changing, then you can propose condition monitoring circuits. That's what we did. So in this slide, for instance, we proposed a very simple circuit for VTH and on-state measurement. Okay, it's just a current source and a couple of diodes. Before you run the system, you inject some signals, CMS signals from microcontroller, some turn on and off like signals, and you can measure both the VTH and on-state resistance of the device. And this circuit, or a little bit different version of this circuit, is already used in TI gate driver. UCC 5870 is a high-end EV gate driver. It has dedicated ADCs. I think it has a data sheet of 200 pages. It's programmable. It's like a microcontroller, basically. That's a very high-end. So this condition monitoring part is implemented in our lab. And EV users, they are very much interested in this. I was talking to TI guys, and they were very happy with that feature. So using this gate driver, you can monitor the VTH of the device. They didn't put on state, but at least they put the VTH. So the user, if they want to do condition monitoring through VTH, they can do it. Like you have this provision in this gate driver. And we try to do online measurement of some of the parameters also. Again, we use the same gate driver. We use the DSET circuit. Okay, and try to monitor the on-state resistance in real time. Now, this is for a three-phase inverter, and we monitor 6 devices. And when you do online, of course, we inject the current, the temperature increases, and the on-state resistance increase. So is it because of aging, or is it because of the load? That's very, very difficult to decouple. So what we proposed in this method for three-phase inverter, strictly limited to three-phase inverter, like if all the devices are good, the temperature or on-state resistance should swing, all 6 of them should swing together. They go up and down all together. Now, if one of them is becoming outlier and going higher than other 6, regardless of what your current or load status is, and it means that one of the device on-state resistances getting higher and higher than the others, average. So something is going wrong on that device. Having said that, like doing condition monitoring online is overkilling. To me, it's not necessary. And I think the best time is like, when you run. Can you hear me?
Yeah.
Okay, sorry. I think, yeah, my charge is going down. I'm hotspotting, it's eating up the charge too fast. I think I'll change the mic, like let me change it in 5-10 minutes. Yeah, doing condition monitoring in real time is not very necessary. It's overkilling, or I can even say it's not meaningful. Like when you start the system, you can inject some signals and measure it at room temperature. That's the best. Or like for EV, for instance, when you stop the system after an hour or two in the garage, you can inject some signals seamlessly and you can measure it so that you can isolate the load effects and current effects from the aging. I think that's the best. But if you want to do online measurement, that's possible, and we have done it. But again, I personally don't recommend it because load, is changing all the parameters significantly. Okay, and it's very dynamic system, and keeping track of the parameters is possible, but interpreting the aging while the parameters are dancing is not easy. Our real estimation, we'll talk about this again. If the user cannot redesign the circuit, or a lot of companies, they just use OEM systems and they still want to do condition monitoring, but they cannot change software or hardware. So in that case, like, we recommend them using remaining useful lifetime estimation, especially if they don't want to change the hardware. Like for instance, there's an automotive customer right now. They've been asking us to do something like this. They are not okay to change the hardware, but they said they can change the software. So in a microcontroller, you can run, different algorithms like Minor's rule, like, rainfall counting. Different aerial algorithms can be integrated to the system. So here, basically, if you measure the current, temperature, bus voltage, frequency, you empirically, like, monitor the status of the device. Again, you're kind of blind here. It's a smart counter. Okay, you don't actually know the status of the device, but you're predicting. Okay, if this is the use case, then your REL should be 80%. Now it's like 70%. Let me give you an example. Like for instance, when I buy a tire, um, the the company says, the mechanic says, like, the warranty is 60,000 mile warranty. Okay, but depending on how aggressive I drive, depending on the road conditions, depending on the load conditions, this 60K might be like, 40K. Like in one of my tires, I think I had to replace it around 25K, and that was designed for 60K mile again. Okay. So again, depending on how you use it, or if there's any mechanical problem in your car, that can be like way lower, and it's possible to estimate it based on the operating conditions. That's what we do. But again, this is not as accurate as condition monitoring, but it's, again, better than nothing. And lifetime extension, we talk about this. Again, if you think that your device is in trouble, then, for instance, if it's a three-phase inverter, you can change the PWM scheme and you can reduce the thermal stress on the upper string or lower string, depending on where the weak device is. Okay, so assume that, like, this upper device in the middle is weak, then you can shift the thermal stress on the bottom devices, switching from space vector PWM to some of the DPWM PWM schemes. So same thing for some of the DC-DC converters, like for interbit converters, for instance, if you have multiple channels, then you have this option. You can shift the stress from one channel to other channels, okay, and provide some sort of thermal relief to the weak device till the next possible maintenance. So as you can see on the left-hand side picture, like the temperatures are close to each other, both channels. But if one of them is like weak, then through another control loop, a third loop maybe, you can shift the temperature from 56 to 48 so that we can extend the lifetime of this weak device a little bit longer. Of course, in this case, the left-hand side device will die faster. So that's why I said these are not meant for continuous operation. These are, last-minute emergency case algorithms. Any questions so far, guys?
So in this particular example, you are looking at, let's say, are you looking at the temperature of the MOSFETs and sort of whichever temperature is going up, you try to push more power on the other phase? What is it you are, or you'll be looking at the RDS on?
We look at the on-state resistance, and depending on the on-state resistance level, like how much it's increasing. Is it like is 10% higher than like average or 15%? Then we adjust the current sharing. Instead of sharing the current 50-50 or 33-33-33, then like we change the percent based on the on-state resistance shift.
If it's a simple parallel device, like not parallel phases, like let's say parallel several discrete devices on board to increase the power rating. Is there a way to do, because paralleling directly also has these challenges, that some device takes up more current and can age faster. So is there a way to then in parallel devices also try to do this?
In parallel devices, we haven't tried it, to be honest. But like, in intermediate converters, if you have multiple channels, you have options, then you can do it. In parallel devices, we haven't tried it. In parallel devices, that's also not that easy, right? You've been driving them from one single point.
Right.
So that may not even be feasible.
Yeah. Pooja Sharma has a question. Yeah, go ahead, Pooja.
Uh, yeah, so thanks for this wonderful, this is going on very, great. So my question is very general, like I think you have explained it in RUL when you was, the third section you were explaining. So my question is like, if we don't have the facility to do the accelerated testing to find the reliability. So what you have said in your RUL explanation is that like in the controller we can put the algorithm and keep monitoring the health of the power device, right? The power devices which are there. Is that correct understanding? Like
That's correct. Like, the most challenging part of this RUL estimation is power cycling test. And for some of the projects, we did them in-house, which is the most time-consuming part of it. But yeah, the good thing is some of the manufacturers, they do provide the power cycling lifetime of the devices. Okay, so you can directly use it. You don't have to do this accelerated aging yourself.
okay.
Now,
Yeah. So in their
they do
product that
most,
is automatic.
they do provide it to mostly big customers. Okay, now if you approach them as a student or in a university, I don't know whether they will do it or not, but if they do, it will be a big relief because you can skip the aging part and directly use their data. That's one thing.
Okay.
The other thing is, like in some of the systems, you have access to temperature and even junction temperature estimation. That makes life super easy because otherwise you have to, in real time, calculate the losses and you have to indirectly estimate the junction temperature. So these two things makes life super easy. Like if the system has a thermal sensor which represents junction indirectly at least, and data like the aging data from the manufacturer. So for instance, for our upcoming project, like we asked them if they can find it for us. So they reach out to manufacturer and they've been waiting for their response. Again, this is not a straightforward question for manufacturers. For some reason, they don't share this. Even if they share it, it's confidential. It goes to only company. They can't share it with others.
Okay. Yeah. Thank you, Professor Akin.
So right now, my charge is going down. I'm going to switch microphones from cell phone to computer. Okay, just give me a second.
Sure.
Can you hear me?
Yes.
Is it clear?
Yeah, it is clear.
Okay. I'm using the phone speaker right now. Sorry guys, again, my Wi-Fi is down today, which is not very common. Like, I mean, this happens once or twice in a year. And it happened today. So, lifetime extension, we talk about this already. Okay, let me talk about some of the ongoing projects we have in the lab. So one of the project was a customer came us and asked us they potentially can use devices from Infineon, Wolfspeed, onsemi, and ST. These are like TO263 silicon carbide devices. Like which ones are most reliable? That was the question. Because like this company, they were super sensitive. They are super sensitive about the reliability, and they are known with their reliable tools for the past 30 years. They make power supplies. And then we listened to them, and then after that we identified 5 tests for their applications which mimic their field conditions, which are listed here. And we took like 20 devices from each company, vendor, and started these tests. Like for each test, I think we used 20 to 40 devices. Okay, so we killed tons of devices for this test. And we run all these products, like the devices, under the same conditions. And then we monitored like multiple parameters through curve tracer. And as you can see, like here, for instance, under the same condition, when the ray VTH is unstable, the others are okayish. Okay. So this is just an example, snapshot, okay, from different tests. And then we did very comprehensive failure analysis, like the customer was asking, okay, why this is happening, what kind of gate they are using, is it trench or planar, this, that, and can we monitor, like, you know, the defects. So we have all these tools at UTD, and we did some detailed FA analysis for this particular project. And then we created the chart. Now, I'm not going to say which company is good, which company is bad. Of course, I don't share these kind of things, but vendor D overall was better than the other. Like we at least have some like red flags for some of these companies. Okay. So yeah, this was an interesting project. And still we have some similar requests, like for GaN devices under very high temperature conditions, like, you know, which device is more reliable than others. Of course, if you look at these devices, package or gate, from gate or package perspective, they are quite different from each other. Okay, now, when you look at, you know, the high level, they look similar. All of them look similar, but when you zoom in and look them in detail, I mean, there are tons of differences. Okay, and they make them, you know, more reliable or less reliable. Some of them, they optimize the cost. That's why, like, they minimize the material, for instance. Some of them, they overuse the material to make it more reliable, but can be more expensive, vice versa. But with the JEDEC standards, for instance, when you run 1,000 hours, all of them looks fine. It doesn't show which one is most reliable, but if you, like, go beyond the JEDEC standards and push them a little harder, then you can easily see which ones are failing first. In terms of reliability, JEDEC does not mean too much. JEDEC, of course, I mean, they should satisfy JEDEC, right, to be in the market. You need to go beyond it. Another project we are working on right now. By the way, do I have time? I have 5 minutes.
Yes, please. Yeah.
Okay. Another project is active discharge of DC bus capacitor. So in case of an accident, you have to discharge the DC link capacitor in less than 5 seconds. That's a standard. Okay, because, like, the driver or passengers may get shock. So it's a requirement, and some of the EV companies, they discharge these capacitors in each and every key off to protect them, technicians, maintenance crew. But in order to do this discharge, typically what they do today, they use a discharge pad like power resistor and MOSFET. Okay, this is traditional solution. And what we propose is, if you're using a silicon carbide inverter, one option is to discharge the capacitor through the motor. Okay, but that's slow, and you may not meet the time to discharge it. So what we proposed is, okay, don't use this discharge pad. I mean, no power resistor, no MOSFET, no gate driver. You can discharge it through the inverter itself. So what we do here, from one of the legs, or you can parallel legs, it's up to you. You can turn on one of the devices. For instance, in this slide, the upper device is fully turned on, silicon carbide, and the bottom is partially turned on. So this is operating in linear mode to limit the current. Otherwise, if you discharge it in switch mode, you will short circuit and you will burn out the devices. To limit the current, like, we've been limiting the BGS in a controlled fashion. And as you can see here, we do apply pulses. Okay, it's not a continuous discharge, and each pulse is limited to 2 microseconds. So it's a frequency modulation, so that this assures device the junction temperature does not exceed a certain value. Okay, otherwise, like, we burn a lot of devices by the time we figured this out. It's not that straightforward, but it's doable. And now we are very confident. We tried this with 4 different vendors, discrete devices and power modules, and we can safely discharge the capacitor through inverter legs in 1 second. Okay, so this is how the setup looks like. This is the microcontroller. This is where we locate power module or discrete device to discharge the capacitor. This is the DC bus capacitor. And this is the gate circuit, gate driver circuit for adjustable voltage. And eventually this circuit will be a part of a gate driver. Okay, like we work with a semiconductor company, so they are going to put this circuit into their gate drivers. So this power resistor is used for charging the capacitor. Okay, not for discharge. We can also, like, replace this with a switch as well. So we heat the device on hot plate, because when you discharge the capacitor and power module temperature will be around like 80-85 Celsius while you have an accident or when you stop your car. Okay, the temperature of the power module will be high, and when you discharge it, the test should be realistic. That's why we heat it up, and then we discharge it. How many times? Like, we charge and discharge it 200,000 times, and we didn't notice any issue on the power modules. Like we've been monitoring the power module and discrete devices in the curve tracer, and it seems perfectly fine, even after 200,000 cycles. Okay, and we don't see heating in the system. And again, we discharge, as you can see here, we discharge it in 1 second. The standard is 5 seconds, but for some reason the sponsor pushed us for 1 second, and that's doable. If you want to do it like 2, 3, 4 seconds, that's even easier. Okay, any question regarding this, guys?
So, Professor, I just want to understand what you're doing. You said that one of the devices you are keeping continuously on, and the other one you are keeping in linear zone. Is that right? Did I understand that?
Yeah,
Okay.
that's correct.
And how you're ensuring the one device that is to be kept in linear zone? You're just playing with the gate voltage, or what are you doing exactly?
Yeah, as you can see here, the gate voltage is somewhere between 4 to 9 volt.
Okay,
A
okay.
little bit device dependent.
Right.
That's the biggest challenge. You need to find the sweet spot. Okay, the gate voltage level, and you need to figure out this modulation scheme. So once you combine them, this can be done.
Right. And typically, you are able to, you have a target of 1 second, but you are able to discharge it within that, even before that, like with 2 microsecond pulses, right?
Yes, that's correct. Again, 2 microseconds, just to ensure that the junction temperature does not overheat. And during this discharge, I think we were around somewhere between 84 to 94, I guess. Not very hot.
Right. Okay.
It's a killing point. I mean, if you can control the temperature, then you're safe.
Right. Right.
And then I have one more time is over, but let me quickly wrap this up. So again, DH toll in this accelerated aging setup, flyback circuits, right? I mean, these are used for charger applications, like small charger applications, very common in QR flyback. That's one of the most common circuits. And these days, people use GAN devices, or manufacturers they're pushing GAN devices. Now here the motivation was, now because of this leakage inductance here, we had a spike. Okay, now one solution to eliminate this spike is to clamp this spike, okay, with some diodes. That's one option. But when you clamp it, your efficiency goes down. So the sponsor was saying, like, what if I use GAN and do not clamp it, or clamp it at higher voltages? Then will GAN be better than silicon devices, more efficient than silicon devices? Because GAN has a transient withstand capability. It doesn't have an avalanche capability. But if you look at the tolerance of GAN, it's higher than silicon typically. That's very manufacturing dependent parameter, but can be higher than silicon. Silicon goes into avalanche mode and you lose the control here. So that's something we try to understand. And if you push the limits of the GAN at max temperature, max peak current voltage, then are you going to damage the device? Like while you're trying to take the advantage of GAN, will this make the device bad? That's what we were trying to understand. And when you look at the classical parameters, they don't change much. But when you look at the dynamic on state, I mean, it's increasing. And this is the setup I mentioned earlier. So this is the GAN device daughter board sitting under power resistance for microheating. Okay, and we stream current and voltage data in real time to measure the dynamic on state resistance at very high speed. And as you can see here, this is a 650 volt GAN, and if you clamp it around 650 is like 700, push the limits of the device, okay, to maximize the efficiency of the system. then what happens at max temperature and current. So as you can see, like, the dynamic on-state resistance is increasing a little bit. So, I mean, this doesn't kill the device, but the efficiency might be going down a little bit. So this is an ongoing test. I mean, I don't have a clear conclusion yet. And we don't have a, remarkable shift in on-state resistance, like dynamic on-state resistance, unlike dynamic on-state resistance. The other parameters seem stable, nice. But dynamic on-state, because of the, the hot electrons and traps, it keeps increasing, and that can potentially reduce the efficiency throughout the lifetime if you push it this way. So this is, again, very application-specific aging test, okay, for flyback applications. So this was a test vehicle. Yeah, that's the another project we are running in the lab these days, and that's pretty much it.
Okay. Thank you so much, Professor Bilal. It was a really fascinating talk. So many interesting things you covered. I know it's past midnight for you, but if it's okay with you, maybe you can see if there are a couple of questions, and then we can go ahead. So, are there any questions from the audience? I think someone had a question in the chat box. Okay, so there was a question from Vanikar Prasad, which says that I think you showed on one slide, I think it was the first project that you were referring to, where you were testing various devices from different vendors, where you selected a certain number of devices. So the question is, how do you decide the device count to be tested for reliability analysis? Is there a general guideline for selecting what sort of size of samples you are taking?
Well, generally, like, rule of thumb, people, they like test 20 to 40 devices, but this is not a rule or standard. Like, you can use like even higher number of devices. I know some of the semiconductor companies, they've been testing way more, like, 60s, 200s. But, to understand the behavior of the device statistically, I think somewhere between 20 to 40 is good. So this is something we decided together with the sponsor. Okay, more the better, but of course you have your practical limits. Now in papers, people mostly put like, 1, 2 samples. I mean, I understand these are, challenging things, not easy, but I think it should be more than that. Like 20 might be too much for research papers also. But 1 or 2 may not represent it.
So if you can explain the setup here, you have those fans to quickly cool down the devices after heating them. What is the setup doing?
Yeah, this is DC cycling. They are cooling down the device. Because if you don't use cooling, then the test takes very long, right? Because
right.
Again, these tests, like, they may take a month easily, and you should, like, quickly finish the cycles. And
Right.
one way to accelerate it is like actively cooling it.
Right. So that you don't wait for it to naturally cool down, then it takes a lot of time.
That's correct, yeah.
So another question is, when you said you had a table in the next slide where you were comparing the different, let's say, devices. You said that, let's say, this device has a poorer gate oxide, this one, reliability, or a package reliability. So what is the metric, what is the number, let's say, you're looking for when you stop the accelerated tests?
Again, there is no standard here, but say, for instance, if 8 out of 20 devices failed, okay, then I say poor. If it's like 1 or 2, I can say maybe, like, it can be neutral, because I've been pushing the limits. But if it's like, half of it, of course, yeah, that's poor, right?
And now failure itself is defined as like a complete breakdown of the device, like
yes,
how is okay.
yeah. Again, you can define it yourself. Like some people, they define, for instance, if on state exceeds like 15%. You may count it as a failure also. Okay, it's up to you. It's how conservative you are.
Okay.
Here, like we prepared this chart based on the total failures.
Okay.
Okay, but it's up to user.
Okay. Okay. So, other questions from the audience? Any other questions? If not, maybe just I have one final question and then we can wrap this up, Brother Bilal. So, I was just curious, for space applications, you have this radiation-related concerns of the devices, right? So, if for reliability of our devices in space kind of applications, what kind of tests would be most relevant?
For radiation, I haven't done it myself, and it's because like radiation testings are very complicated and can be done with very expensive tools. Here, I know some of the companies they've been doing it, and they do work with national labs. Like they also don't have those tools, so they reserve the lab like for 2-3 days, and they pay like around 50K for those 2-3 days. Those are very expensive systems. So basically, they're bombing with I don't know, applying different radiation like neutron bombing. I haven't like worked on that. I was planning. There were some requests. Since like it's not something I can put in my lab, that was not very attractive for me. So
But
that's why.
essentially, you would look at the same device parameters for the degradation, right? Like say RDS on going up or things like that sort, right? How that changes with a certain dosage of radiation, right?
I'm not super familiar with the failure mechanisms, and I don't have benchmarks like which parameters are changing and how they are changing, why they are changing under those conditions. That's why I think I'm not the right person to answer this question.
Okay, so let's see. There's a final chance to ask any other questions to Professor Bilal. Audience, any other questions? Okay, so if not, then Professor Bilal, thank you once again. Okay, Pooja, you have something?
Yeah, so just last question that is also related to the product reliability. So Professor Bilal, so this is basically when we are calculating the reliability of a of a product. So it has the power section and the controller section, and the reliability of a product is like dominated by the power section. So is it a good practice to ignore the controller reliability or the control section reliability to decide the product reliability?
So you're asking system level?
System level, yeah.
Well, system level again, that's something I do have some requests from the companies these days. I haven't done it myself. We tried some methods, okay, but uh, that's a very tough problem, to be honest. Because like now you're talking about if it's a one single component, like you can create different issues in the device, okay, and you can define your own failure and you can monitor it yourself. I showed like maybe like 6-7 different tests we do very often for just for power semiconductors, okay, and package gate related issues. So I can like monitor them very accurately. Now imagine you have tons of components on the system, like you have capacitors, you have solders, you have traces, you have different ICs. Now, like creating different faults, like controllers, okay, and combining them all together at the system level and trying to identify them, uh, that's not easy. So the only solution I can think of for those kind of system is AI. Like AI can learn the system and raise the flag for anomalies. If there is an abnormal situation, I think AI can raise the flag. But even there, if you want to train AI, that's also not that straightforward. Like how we train AI, for instance, I did some AI work. Like again, you create some of the issues artificially, and you teach AI, okay, this is fault, this is, tolerable fault, this is okay fault, this is too much fault, this is intolerable fault, different levels and different types of fault, which is very painful. Now, if you do this for each and every component, I mean, that's not practical. Okay. Now, AI, if you don't want to classify it, it can tell you whether it's normal or abnormal. Okay. But if you want to classify it, that's super painful. So system level, that's a difficult problem. Like I don't have a solution as of today.
Okay. Yeah. Thanks, Professor Bilal. Yeah.
Mm-hmm. Yeah.
Okay.
I mean,
Thank you.
Looking at it, yeah. Okay.
No, go ahead.
Yeah, I mean, we do look at the different aspects of it. I think I work on motor faults also for several years, and AI seems to be the ultimate solution for those kind of things. Some of the faults, they are very hard to keep track of. But AI, it's very good at recognizing the patterns. Like it's not very easy for us. Modeling it is not very easy. Behavior is very complicated for us, but for AI, I mean, it's relatively easy for it, and we had very high accuracies in some of the conditions. Now, if you can use your lab results in the field, which is another challenge, because lab is, very hygienic, ideal lab conditions. When you go to field, you have different temperatures, you have different vibrations, you have different this problem, that problem, interference. It's like a jungle. So your trained model may not be sufficient for field conditions. But if you can assure it, there are some tricks for those also, like training the last layer in the field, kind of. Yeah, then that's doable. Like I believe, 3-4 years later, we'll be talking about very stable, successful AI solutions.
Yes. Yes.
Okay, so it was excellent talk, Professor Bilal. As you explained right at the start, reliability is a very important aspect. It's probably the most important aspect for most companies and product manufacturers. So it was really great, and there's so many interesting aspects that you brought out. So let me end by again thanking you once again for giving this talk so late in the night for you. So apologies for that, but thank you. And if you have plans to visit India anytime soon, please, we'll be very happy to host you next time in person at IIT Bombay, or maybe we'll bump into each other in some conference soon enough.
Thank you very much.
Thank you. So I'll conclude the webinar here. Thank you, everyone.
Thank you.